Welcome. The semester certainly is moving along, I hope for you as well as for me. The picture here, this is a old building that I really loved in Akron, but they tore down. I can't believe they tore down such a beautiful old building, but they did. And so I'm featuring it on today's slide. Anyway, this is Advanced Statistics 2. This is Class 6, Moderated Regression Categorical. We've already covered moderated regression continuous, and so we're really just building on that last class, except for this class, the moderator variable is a categorical variable instead of a continuous variable. I actually think categorical variables are easier because it's easier to understand the moderation or the interaction. But that's what we're going to be covering today, moderated regression categorical. And of course, again, as with last time, in your book, in the field book, they do moderation through process, Hayes's process. We're going to do that later, starting next class. But first, we're going to teach you how to do moderated regression the old-fashioned way, just using SPSS without using process. So we're going to start SPSS approach to moderation without using process, which is something field doesn't really do. And then we're going to go into how to use process to look at moderation with a categorical variable. And of course, again, moderation is just the combined effect of two variables on another, is known conceptually as moderation, and in statistical terms as an interaction effect. And you can go back and review, if you want, the last lecture, our discussion of moderation and interactions. Again, this is from the wiki. I'm not going to read the whole thing again. I think it's very good. I'll just let you take a look at it. If you want, you can pause on this slide. And of course, last time I went through interaction, first moderated regression, and talked about, is there a difference? And my opinion that there is, but that most people sort of really don't recognize this difference. And again, this slide just continues with the argument I made last time, that there really is a difference between an interaction variable and a moderator variable, that the two are not necessarily the same thing. But again, if you're interested in this, you can go back and review the last lecture. And of course, we talked about, interactions. Here's a simple interaction. Ability and motivation interact. You can see this X represents the interaction. So ability and motivation interact, and they cause psychology grades. A more common one was this predicting college performance or GPA from general mental ability, where the interaction involves demographics, which here clearly is a moderator. So we have demographic variables such as race, sex, age, and those interact with general mental ability to predict GPA. And the interaction here is more clearly a moderation, where the demographic variable changes the relationship between GMA and GPA. And then if you remember, we also talked about more complicated interactions, such as this one, where the demographic variable interacts between GMA, or moderates the relationship of GMA on job knowledge, and then also moderates the relationship between job knowledge and job performance. So there's sort of this double moderation. I mean, this is really a model with both mediation and moderation. And of course, last time we did where we had two continuous variables. This time we're going to do interactions with one continuous and one categorical variable. And so at least one or more of the variables in this case are categorical, and they're interacting with either a continuous or a categorical variable. Note the situation where we'd have two categorical variables is actually the analysis of variance situation, especially if both variables are manipulated. or even if they're not, we would have a quasi-experiment. So when we have two categorical variables, we can still handle it by regression, but more typically we would handle that situation using analysis of variance. So typically what we have in this situation is one continuous and one categorical variable. So we're going to do one continuous and one categorical variable. And what's interesting is that matches up with one of the more common dilemmas we find in psychology, the issue of are tests fair or do tests have differential validity, which is sometimes called the Cleary model of regression, or Cleary model of fairness. So this has a lot of application. It has a lot of application to those of you in almost any field who want to be involved in assessment, because this model where we have one continuous and one categorical variable is, again, the classic fairness model. We have a test that's predicting some criterion, and we're asking, is it moderated by some demographic variable? And that's the classic fairness model, sometimes called the Cleary model. And so here it is again. We're going back to a slide we already showed you. The classic situation or dilemma in psychology is often, is a test fair for all different groups? Does it have the same validity for all different groups? And that's this classic moderation model where demographics moderates the relationship between the test, in this case general mental ability, and the criterion, in this case GPA. But again, this could be any test. It could be the Big Five predicting depression. It could be a depression measure predicting suicide ideation. And we want to see if that test predicts equally for all groups or is fair for all groups. This is especially important when the demographic variable is what in the United States we would consider to be a protected class. Okay, when we have a categorical variable, we have to do what's called dummy coding. I don't know if you talked about that last semester, but we have to dummy code our categorical variable. I don't think this is that complicated, but a lot of people struggle with it. There's a number of different ways to code categorical variables. We're really just going to deal with the simplest approach. I don't think field really goes into this in any more depth. However, if you are interested in all the different ways to code variables, you can always go online and take a look for other experts or authors offering their advice. Also, you should have really learned about this last semester, because in analysis of variance, we often have to do dummy coding as well. So especially to look at contrasts. So I don't know what you learned last semester, what you didn't, but you may have learned about dummy coding last semester, since it's an approach to setting up contrasts in analysis of variance. But this is probably the most difficult thing about moderated regression, the dummy coding, and it's actually, I think, very simple, but some people struggle with this idea. Okay, so that brings us to, as I said, one of the most common dilemmas in psychology, what we call the differential validity hypothesis. Really, that's an interaction hypothesis. It says a test might be valid for one group, but not for another group. For example, a common claim has been that intelligence tests are valid for white Americans, but are not valid for African Americans. That's basically then looking at a categorical variable of race. We usually code that black-white. So we use the term black here and white. This would be what's often hypothesized to be the line associated with white Americans. The test is valid when taken or administered to white Americans. This would be the line for African Americans. The test is not valid when administered to African Americans. That's the common differential validity hypothesis. You can see that expressed in a regression equation here, where we say y equals some a, or a constant. In field would label this b sub 0. I think it's more common, especially in the differential validity literature, to label this with an a, plus a beta weight, b1 times our race variable. And we're going to have to dummy code race, of course, plus b2 times the test variable, our x, plus b3 times the interaction of race and sex, or race times sex. And if this a is significant, it just means the intercept of the lines is not 0. If this b1 is significant, it means the two groups have different intercepts. So this b1 is going to be a test, really, of do the groups have the same intercept or not. This b2 here is the test valid for both groups combined? And then the b3 is going to be a test of, or a measure of, an indicator of, does the test have differential validity? Is there a difference in the validity for both groups, or between the groups? So that's our common differential validity hypothesis that we run into in psychology all the time, really. And you can see that that's basically going to be handled by moderated regression. So we handle investigating differential validity through moderated regression. This is often called the Cleary model, after Ann Cleary, who developed it. So you can see I drew it this time dropping the scatter plots to make it a little easier to see. So again, let's make it this time sex instead, even though we have an R down here. So perhaps this time is the line for females, and this is the line for males. Maybe we have a test of sexual harassment, and we're trying to predict some kind of reaction to a sexual harassment incident. And we find our test is valid for females, but not valid for males. This then would be the regression line for females. This would be the regression line for males. Again, the equation is the same, a, the constant, plus b sub 1 times, in this case, sex, plus b sub 2 times the test, the sexual harassment measure, plus b sub 3 times the interaction of sex and the sexual harassment measure. And again, if this term, the b1 term, is significant, it means there's a difference in these two intercepts. If this term is significant, it means there's a difference in the slope of these two lines, which means that there's a difference in the correlations, basically. That's not totally true, but it's close to true. Okay, and again, now the situation does not have to be a test predicting a criterion. This is just one of the more common issues we run into in psychology, and certainly one of the more fiercely debated. So this is an example of what would be called just intercept bias. So as you can see, in this case, we have a test and it's predicting job performance. And we have the regression lines for the two groups. You can see there's a difference in the intercept. The slopes are equal, the slopes are parallel, but there's a difference in the intercept. So in this case, here's the minority regression line, here's the majority regression line. The slopes are equal or parallel, but there's a difference in intercept, which means that for the same test score, we're predicting different levels of performance. So for the same test score, for a certain test score for the majority, we're actually predicting a lower level of performance than we would for a minority group member. For the same test score, a minority group member will have a higher level of performance than will a majority group member. And so that's classic intercept bias in a moderated regression. And there you can see now the prediction for the minority. Again, with slope bias, it's a little more complicated. This would be a situation where we have slope bias. You can see the line for the majority, the regression line for the majority, the regression line for the minority group. The regression line for the minority group is more extremely sloped. So actually, in this case, the correlation would be higher for the minority group. You can see that results in different predictions at the same test point. Now, this would be an ordinal interaction. So this would be an ordinal interaction. And again, as we said last time, one thing about ordinal interactions is, in theory, you can get rid of an ordinal interaction through some type of transformation. You might not know what that transformation is, but you can get rid of the ordinal interaction through some type of transformation. But this would be an ordinal interaction. And of course, a disordinal interaction, again, would look like this, look like an axis. We don't have a disordinal interaction here. We have what would be called an ordinal interaction because the lines don't cross. They sort of meet at the intercept. In this case, the intercepts would actually be equal. It's the slopes that are unequal. So that would be an example of slope bias or slope differences in a moderated regression. And we can see, again, that the predictions, one of the issues is, of course, our predicted values for the same test value would be different for the two groups. And here's just some more of my bad drawings. So this just shows you a test can be a valid test with group differences. So this would be a valid test. It has group differences, but it's a valid test. You can see there's no, the regression lines are actually the same. If that was true, then in our classic sort of regression approach, our A value would be significant. Our B2 value would be significant, but our B1 and B3 values would be non-significant. Now, you could also actually do this by calculating the separate regressions and then testing using a t-test to see if these beta weights and the constants were equal or not equal. But of course, it's much more efficient to run this using a moderated regression, like right here. And again, this is the same thing, but here there's no group differences. So the test is equally valid for both groups, but actually there's no group differences. Again, in this case, A would be significant, B2 would be significant, but B1 would not be significant, and B3 would not be significant. I hope you're following that, understanding it. If not, please bring your questions to the discussion group. And this pretty complicated drawing is where you have equivalent slopes or equal validity. The slopes are the same for the regression lines, but you're under predicting one of the groups. In this situation, the one line would be the white line, the other line would be the African American line. So we're looking at race, and you're actually under predicting African American performance. This is the common situation of using the SAT to predict the GPA. If that was true, then again, in terms of our regression line, everything would be significant. Our constant would be significant. Our B1, which represents the differences in intercepts, would be significant. Our B2, which says, is the test valid, would be significant because it is valid and it's valid for both groups. Our B3 would be non-significant. I think I said that everything would be significant, everything would not be significant, as you can see. The B3 would not be significant. So the B3 would not be significant because the regression lines are parallel. The regression lines are the same. The test has equal validity for the two groups, but it doesn't result in the same predictions for the two groups because the intercepts are not equal, even though the lines are parallel. Okay, so in your book, they actually go through a pretty extended discussion of dummy coding. They cover dummy coding from 377 to 382, so I'd encourage you to review that material. It's certainly important. But again, I don't think dummy coding is all that difficult. I don't know why people struggle with it. We'll start and we'll consider the simple case. The simple case is, of course, when you have a dichotomous variable. A dichotomous variable means you only have two choices. Now, we know in psychology today, especially from a social justice perspective, we often consider there to be many more than two choices for some of these variables. Nevertheless, the reality is in our research, we often end up dichotomizing the variable or ending up with two choices. Also, for various historical and also sometimes legal reasons, we often end up with two choices. So demographic variables often end up being dichotomized. Of course, there's other variables that would be dichotomous variables as well. So one variable might be sex. If in our study we only have two options or two groups for sex, males and females, then we have a dichotomous variable. And so we can code that 0 and 1, because that's what we're going to do. We're going to code dummy variables 0 and 1. So we have to pick one group to code 0 and one group to pick code 1. Of course, it's important to remember which you do with which. But if we have more than two options for our sex variable, then the coding gets a little more complicated. As I discuss in the book, you can always turn it into a series of dichotomous variables. So for example, if you have three options, your first dummy variable would differentiate option 1 from option 2, and your second dummy variable could differentiate option 1 from option 3. So review that in your book, what happens when you have more than a dichotomous variable, when you have more categories. Generally, what you do is you create categories minus one new variables. So if we have 6 categories, we'd have to create 5 new variables, each of which are dummy coded to totally cover that variable. So I hope you sort of see where that's going. If not, please review the book. They do a pretty good job of excellent job of discussing it. There's also a lot of online resources. For us here, we're just really going to cover dichotomous variables. So again, say we have sex coded male, female, or we have race and we've coded it a minority group member, majority group member. We have answers to a test and we've coded those true, false, or correct, incorrect. Or we ask people if they agree with something. I agree, I do not agree. Or if we're looking at politics and we again reduce it to 2 groups, Democratic, Republican, leaving out independent, etc. As long as it's a dichotomous variable, only 2 options, we can code one option 0 and the other option 1. And that's all really the dummy coding is. Of course, in the case of a dichotomous variable, it's the simplest. I had to re-record this particular slide because the phone rang. That's the kind of great service you get here. Even though the phone rang, right at the end of recording this slide, I am re-recording it for you, so you don't have the phone ringing. All right, anyway, in our data set, I did dummy code a number of variables. The variables I've dummy coded for our data set, or for the COVID death data set, include for each of the states, I looked to see whether they were in what would be considered the North or the South. There's actually an official designation of this, although I threw in a couple extra states that are not technically Southern that I thought should be treated as Southern. But so if a state was a northern state, I coded it a 1. If it was a southern state, I coded it a 0. Some people have been interested in the political party of the governor. So I coded a Republican governor as 0, a Democratic governor as a 1. And then there was even an article in Journal of Applied Psychology, but there's been a lot on Twitter and in other social media outlets about female presidents of countries or female governments running countries being more successful in handling COVID than male-run governments or male presidents. And so in Journal of Applied Psychology, there was actually an article that looked at male versus female governors. So I coded male governors a 1 and female governors a 0. There's really very few female governors, though, so it's questionable whether we can really look at this variable. And in reality, for the US data set, there's no correlation. So we're not going to run any analyses with it. But we did do these dummy codings. All right. So anyway, our steps to do this in SPSS is that first we have to create our dummy coded categorical variable. Once we do that, we then have to create an interaction between the dummy coded categorical variable and the continuous variable. We can do that again by multiplying the two variables together. It's a simple multiplication to compute a new variable. Now, some people, before they do that, center the continuous variable. I do not. So before I create the interaction, before I multiply the continuous and the categorical variable together, I don't center the continuous variable. I don't center it because I don't see what the point is in this case, because you're almost always going to be regarding the moderator variable as the categorical variable, or you're almost always going to be regarding the categorical variable as the moderator variable. And the categorical variable has a 0 already. So I don't see the point in centering the variables. Although again, there's actually people who center the dummy coded categorical variable as well. And I really don't understand the point of that, but there's people who do it. So you can do it. You can center both variables. I just do not center either variable when I'm looking at an interaction of a dummy coded categorical variable and a continuous variable. Once we create the interaction, of course, then we can run our regression analysis. So again, it's the same as our simple linear regression. In SPSS, we just say analyze regression linear, and it'll run our regression analysis. We'll get a menu, and we can pick our choices, and it'll run our regression analysis. Okay, so now what we're going to do is we're going to return to our COVID data set. And as I said, I dummy coded political party, Republican governor equals 0, Democratic governor equals 1. So political party was dummy coded. We have our density per mile variable. Our dependent variable is going to be deaths per million, COVID deaths per million. And then we've created now an interaction between the party of the governor and the density of the state. So this is our interaction variable right here that we computed. And now we're going to enter into the regression. We put it in, and what I did here again, as I discussed last time, I did this in 3 steps. So it's basically, again, what Field calls a hierarchical regression. So I ran a hierarchical regression. On step 1, I actually put in the political party. Probably should be reversed. Probably should have put in density per mile in the first step. But I put in political party in the first step. Then in the second step, I put in density per mile. And then, of course, the last step, we have all 3 predictors: political party, density per mile, intergovernment, the interaction of government, political party, or governor, political party, and density. And then actually in each of these, we also have, of course, a constant. And again, the dependent variable, deaths per million. So we can see here, if we look at our model, our R, you can see political party actually is not significant. Density per mile is significant. And then the model that has the interaction is also not significant. So again, here's our R's, our R squares, our adjusted R squares. So take a look at this model. By now, you should be able to interpret them yourselves. You can see, again, that the first model is not significant. The second one is, the third one is not. So the critical variable seems to be density per mile, and really the political party of the governor doesn't seem to make a difference at all. We can go to the next slide, and this is just the complete analysis of variance model. What we can see is the same thing, really, that the second model was significant. The third model is now significant. It's just that the R squared change is not significant. So the R squared change from model 2 to model 3 is not significant. But model 3 is still significant. It's not a significant improvement over model 2. So adding the interaction does not result in a significant improvement over model 2. All right, so our next piece of output would be the estimates of our standardized B's and our standardized betas, our parameter estimates. And of course, we get the estimates for each of our variables. We get our T for each of our variables, and we get our significance levels for each of the variables, or our estimated P's. We can see that political party is non-significant. So hopefully you can see your political party is non-significant. We can see that political party, when we put both political party and density per mile in the model. So when we force both those in together, density per mile is significant. Now this is interesting because remember model 3 was significant, but when we put all three variables into the model, or force all three into the model, so include the interaction, you know, density per mile is no longer significant. I mean, again, that's because you're now controlling for this interaction. So when you control for this interaction, density per mile is no longer significant. But since the interaction isn't significant, I would interpret this, or the way I would say this is, hey, we're just going to drop this model, and we're going to go back as the most useful model to the model without the interaction, which is the one that has density per mile and political party. Or actually, we don't even need political party, probably. We could just throw that out and go to the model that just has density per mile. The interaction is certainly not significant. Since that one didn't work out very well, I ran another one for you. Now, I said I dummy coded north-south. North was coded 1, south was coded 0. And so now I have a regression, and I've run this the more traditional way that I like. I first put in density per mile, since I was regarding north-south as being the moderator. So I first put in density per mile, and then on the second step, you can see I put in north-south, the dummy-coded variable. And on the third step, I put in the interaction of density and whether the state was in the north or the south. Again, the dependent variable we're predicting here is COVID deaths per million. Okay, and so here's our, really first piece of output. Again, it's the model summary. By now, you should be very familiar with this. We have our R. And again, for density per mile, it's highly correlated with COVID deaths. So the R is pretty high. We have our R squared, our adjusted R squared, our standard error of the estimate, our R squared change, our F associated with that change, the degrees of freedom for that F or change statistic, and then is the change significant? So this one's a little more interesting because we can see, of course, the density per mile is significant. When we put in, or when we force in the geographic region north-south, the model, it doesn't result in a significant F change. But when we put in the interaction, the model does result in a significant F change. So this model does result in a significant R-squared change. As you can see, when we move from model 1 to model 2, the R-squared change is only 0.006, which ends up not being significant. When we go from model 2 to model 3, the R-squared change is 0.062, which ends up being significant right here. All right, here's our next piece of output. And I'm sorry that this is so small, but to fit me in, I had to make it smaller because I wanted you to see all of this, and I was cutting off the bottom again. So these again are our unstandardized B estimates, our beta estimates, the T associated with each variable in each model, and the significance level for each variable. So again, with model 1, we were only putting in density per mile. When we only put in density per mile, here's our B, here's our beta, here's our T. We can see density per mile is reaches statistical significance. Our p-value is below what we probably set as a normal alpha level. When we put in density per mile and geographic region, remember this R-squared change was not significant. And actually, north-south is not significant either. That variable is not significant. Now, when we put in the interaction, we find, hey, we do have moderation. We were right. Geographic region moderates or interacts with density per mile. Now we can see that we have only one significant effect, and our only one significant effect is that interaction variable. So now our interaction of density per mile and geographic region is significant, 0.039. It's significant, and what's interesting is the other two effects are no longer significant here. So the other two effects are no longer significant. Now, we know density per mile did relate or predict COVID deaths, but we see that when we now put in the interaction, it no longer even comes close to being significant. As a matter of fact, when we put in the interaction, for some strange reason, the region becomes close to being significant. But density per mile is no longer significant. So that's really pretty interesting. It suggests that, you know, we have to look at this interaction effect. So if we remember back to analysis of variance, if we have an interaction effect, we probably shouldn't interpret the main effects anyway. And clearly in this case, it would be dangerous to interpret the main effect because we should be looking at this interaction effect. Okay, so now what you can see here is I've just created the different regression lines for the north and the south. So for the north, we're going to have, well, really for both groups, we're going to have the constant 965.78 plus negative 0.187 times density plus negative 293.55 times north-south. And remember, north is a 1, south is a 0, plus 1.276 times density times north-south. And it's the same equation for north and south, except you can see what happens. So it's the same equation for north and south, except you can see what happens again. Remember, north-south is coded 0 or 1. So for the north, this becomes a 1 and this becomes a 1. For the south, this becomes a 0 and this becomes a 0. Well, since this becomes a 1 and this becomes a 1, if you remember back to grade school again, basic algebra, we can simplify this and say, we can combine these terms. We can say for the north, our intercept or our constant is now 965.78 minus 293.55, which equals 672.23. And then that's going to be plus a negative 0.187 plus 1.276 times density, which is 1.089 times density. Because again, north-south was a 1. So when you multiply by a 1, it's just the number. On the other hand, south is a 0, so north-south here becomes a 0. So any number times a 0 is just a 0. So this term drops out and this term drops out. And our regression line for the south is just 965.78 plus a negative 0.187 times the density. All right? In terms of understanding this moderation, it can be interesting to look at the correlations by group. So when we look at the correlations by group, we see that the correlation between COVID deaths and density is 0.644 for the north. So this is the north. You got to look at it way down here. Where's my pointer? You got to look way down here. You see, this is the data for the north. So for the north, the correlation between density per mile and deaths is 0.644. If we go and look at the south, the correlation is negative 0.11. So in the south, there's actually a non-significant, but slightly negative correlation between density per mile and COVID deaths. Whereas in the north, there's a large positive correlation between density per mile and COVID deaths. So we can see the moderation very vividly here. South, no correlation between COVID deaths and density per mile. North, large correlation between COVID deaths and large positive correlation between COVID deaths and density per mile. And you can see I've actually then done a little chart here. Again, this is the South. These are the southern states. You can see there, there's some, it's not a really clean scatter plot, but you can also see that there's really no relationship between density per mile and COVID deaths per million. So you can see that there's some states with relatively low density with a lot of deaths. And there's this group of states where as density increases, there's really the deaths is pretty constant. Then there's some states with pretty low numbers of COVID deaths. Those are low density, but there's basically no correlation. And we can see it when we do this scatter plot, or when we plot the data and put a regression line on it. And then this is the north, and you can see for the north, again, there's it's not all that clear, because again, there's, the data is a little messy, as data always is, but there's a pretty clear, strong correlation between density per mile and COVID deaths. And you can see that illustrated here. For the north, as density per mile goes up, COVID deaths go up. All right, we're going to turn to field now, categorical predictors in regression. Often you'll have categorical predictors that have more than 2 categories. I don't know how often that is. I usually try to avoid it, but often you may have categorical predictors that have more than 2 categories. These groups cannot be distinguished using a single variable coded with zeros and ones. Therefore, we use what's called dummy variables. So now we're adding to dummy coding dummy variables. So here he's taken his data set and coded some different festival data. He's coded it in terms of what groups the individual associates with. And you can see he has 4 groups. So as I said before, usually when you have 4 groups, you're going to have to create 3 dummy variables. He creates 3 dummy variables. He always gives no affiliation a 0. For IndyKid, dummy variable 3 is coded a 1. For Metaler, dummy variable 2 is coded at 1. And for crusty, dummy variable 1 is coded at 1. And that distinguishes these different levels of the categorical variable. So you can see you're going through a big explosion here, because now we're going to have 3 dummy variables for these 4 categories, which means we're going to have to create 3 interactions of these dummy variables with whatever our continuous variable is. So we're going to have to create not only 3 variables to express the categorical variable as dummy variables, we're going to have to create 3 interaction variables, or a total of 6 new variables. And he says that you can do this using recode into different variables, which you can. So for example, he's recoding music into no affiliation versus crusty, calling it crusty. And all you have to do is take your values and recode them. So he's saying if it was originally a 3, it should now be a 1. And that's how he does it. And then he does run an analysis. We'll show you some of his output. So here's his output from his situation with this categorical variable. The predictors going in are a constant, and then no affiliation versus IndyKid, no affiliation versus crusty, and no affiliation versus metaler. And you can see that overall this model is significant. So again, by now, I hope you can read these. So by now, I hope you can go through and read these pretty quickly, and you can see that the model is in fact significant. Then we can look at our different coefficients, and we can look at then sort of which categories are significant. And you can see that when we look at these, we have 2 of them that are significant. No affiliation versus crusty is significant, and no affiliation versus IndyKid is significant. Now you might ask, can you compare crusty to metaler? Not with this comparison. So again, if you remember back, this is very similar to what you did in ANOVA with contrast coding. This will not allow you to compare crusty to metaler. It just allows you to compare each of these to no affiliation. And then he gives you his bootstrap for bootstrap coefficients, and then he gives you what are called OLAP cubes. Again, if you're interested in this, please go back and look at take a look through the book, read through the book for more details on all these things. Then he discusses how you can interpret the results, which again I think is always nice. Sorry for cutting this off at the bottom, but basically again he reports each of his category variables, the B's and the betas. He reports the R-squared down at the bottom. So again, you can take a look at that in the book. Now you might ask, what happens when we have 2 categories? I might ask that. Well, again, 2 categories, it's probably going to make more sense to do an analysis of variance, because the output is going to be more helpful, but you certainly can do this using regression. So even though it might make more sense doing it using analysis of variance, by now you should be knowledgeable to say, well, aren't they the same linear model? And yes, they are the same linear model. So you can do this using regression. So here we have I just did one more analysis. This actually is 2 categorical variables, or they're dichotomous variables, and I've done it using regression analysis. So in this case, we have 2 dichotomous variables or categorical variables. Now we have north-south, which again was north was 1, south was 0. We have the political party, the governor. Republican was 0 and Democrat was 1. So someone might think, these two variables might interact, or might be interested in looking at whether they predict COVID deaths. Again, the dependent variable here is deaths per million, or deaths in the population per million. Again, the state population, of course. This analysis is being done at the state level. We put in the constant, we put in north-south, we put in political party. You can see none of these are significant, which isn't very interesting. The interaction isn't significant. So overall, we can conclude that really looking at political party, looking at region of the country, north-south, doesn't really make a difference in terms of predicting COVID deaths. Although in our last analysis, we saw it did make a big difference when we combined it with density. And what I mean is that the geographic region of north-south had a big effect, or made a big difference when we combined it with density. Okay, and again, that's the end. We have our friend the straw here again for some reason, but that's the end. If you're interested in, if you have questions, please email them to me at dennisdoverspike@gmail.com. Thank you again.